All right. Hello. So today I'm going to be doing a full review video on basically everything we learned this unit, and this is for test number 3, I believe. And so I'm gonna just basically be going over just like a review of all of the notes we did in class, and then like a little bit of like the application of that. But like, yeah. So basically, we start off by learning about mechanical waves, which is basically just like things moving in a wave like pattern, kind of. There wasn't really any super big definition, but I think that's just like like sound and then like ropes and stuff, whatever. So basically, in terms of this, there were three main things: longitudinal, transverse, and rolling waves. So basically, this he gave the example of a piston pushing a bunch of air particles, and basically they're more bunched up in certain spots because this was moving forward and backwards, and so basically this means the movement of one particle, right, moving back and forth is parallel. So these are like the parallel waves, parallel to the velocity of the wave. So like if we measure like particle movement or whatever, the velocity of this wave is going to be the same direction as the particle movement. So then for the transverse waves, he gave us an example of taking a rope and swinging it up and down. Um, Basically, this is where the movement of one particle or one point on the rope is perpendicular to the velocity of the wave. So as you can see, this would be moving up and down, and the wave would be traveling that way. So it's pretty perpendicular. And then rolling wave is basically just a combination of the both of them, where the particle is going to just be moving in a circle. He gave the example of like a wave in the ocean with like something pushing against it, like that and like that. I don't really think any of these are really going to be in like calculations per se, but I think it might have some questions where it's like, um, where it'll require us to know somewhat what these mean. So, yeah. So I think that's basically it. Yeah, and then just to make sure that we know that like no matter or mass is actually transmitted between these, and it's just particles moving, and then there's just the energy going through them. So yeah. So from this we had a few relationships that we needed to go over. So basically, here's a general like equation sort of sheet. A velocity of the wave is equal to the wavelength over the time period. The wavelength being to where it repeats. So if we have like a wave like this, here to here is a wavelength, here to here is a wavelength, here to here is a wavelength. Um, Basically, and then the time period is the time for it to complete that wavelength, basically. And so that's how we measure the velocity of the wave. Also can be seen in frequency. And the relationship between frequency and period is frequency is the inverse of the period. Period is measured in seconds. Frequency is measured in hertz. Velocity of the wave can be measured in normal velocity units, meters per second. And so this last equation I'm not exactly sure where it's mentioned. I think in the standing waves part, but I felt like it kind of fit in here because it's talking about velocity of the waves. But basically, it's saying the square root of the tension over the linear density is the velocity of the wave as well. And I believe that's true. Yes. Okay. So basically, the linear density then is calculated mass over length of the string. This is like basically um only for strings, I believe, or any. It has to have like the thing that's moving has to have like mass and like a length. This isn't necessarily the wavelength, but basically we could also write this as T over M over L. Yeah. So I think that's gonna be it for this part. That was just kind of a little bit of a thing, moving all the way to superposition. Yeah, just one more thing. He wanted us to be sure. I'll just clear this slide. You want us to be sure that we know what happens when a wave goes around like a post like this, goes higher up. Basically, if it's traveling this way, it'll get reflected back over that way. Same amplitude here, and it'll just go the opposite way. And then if it's tied to a wall that's not going to let this move, then it'll just get inverted with the same velocity, same inverse amplitude. So, yeah. So, the next thing I'll talk about is superposition and wave energy. So, superposition basically is just saying that when two waves like collide, um, they're not going to really like stop each other. They're going to just go through. Like, if we have this as the before, and then the after basically will just be the same waves. This wave will have traveled all the way over here, and then this wave will have traveled all the way over there. So basically that's what he wants us to know about that, and also that um when two waves are going at each other, they will combine amplitudes for basically one instance where the amplitude is the total energy of both of the waves. So yeah. And then in terms of wave energy, it wants us to know what would happen if a bigger rope, right? Like a thicker rope, it has a pulse sent through it with a velocity, let's say just a normal v. What happens when it hits here? Well, then this thinner rope would basically have a different velocity because it has a different amount of energy. And then if we were to reverse that, starting with this rope, it would actually push a smaller wave over here and then also have a reflective wave, because in some ways you can think about this like it being attached to a wall, like that it's going to reflect some of the energy, but combined, this energy will be conserved from this entire amplitude. So basically the energy in these two amplitudes is equal to the energy here. So that's basically that. Also, he talked about constructive versus destructive interference. Constructive is basically when two waves are heading towards each other. Um and they're both in the like positive plane, you could say, then they'll constructively interfere. And then if two waves are opposite, then they'll destructively interfere. And if we have like a wave that's like continuous or whatever, if there's another wave on top of that that's exactly the same, it'll cause the amplitude to be greater. But if there's a wave that is opposite to it, then the amplitudes will actually cancel out and it'll be like a flat line. That was basically that for constructive interference. And yeah, let's see. Okay. So the next thing go over is standing waves. So this was basically just like the harmonics. So of course you have first harmonic, which is a wave vibrating up and down like that. Um, Also called natural frequency. Same thing basically. And the main thing from here was that the antinodes were where it moves the most, and then the nodes were where it moves the least. And so, in terms of calculating the wavelength in this case is going to be um, two times the length of this thing. And that's if it's like a sort of guitar string, something like that. And then as we increase harmonics, then it's just gonna increase the number of antinodes for this setup. And then also to look at like how the frequency changes. Basically, the frequency is just multiplied however many harmonics you have. It multiplies the frequency of the natural frequency or first harmonic. So, yeah, that's basically it. I mean, if we want it in a total or like a summed up sort of equation, I believe he wrote like three. Actually, wait, what is this? That's the safe frequency equation. There was a total relationship here. I don't have it written down, but yeah, whatever. Basically, you just multiply the number to get the frequency. You just multiply it by the number of harmonic times fundamental frequency. Yeah. And so then the closed end, which he said was like a wind instrument with a closed end. So that's a closed end. Basically, the node is going to be there, and then the antinode for the first harmonic is going to be at the mouth. And for this, the wavelength is uh 4 times the length of this tube, basically. And as it increases, I mean, I think you can kind of reason out how it's going to go. But basically, um, we're still adding, I think, half a wavelength here, or half a wavelength every time. But just starting at wavelength over 4. And then if we have a tube that is open on both ends, then the node is going to be in the middle, and it's going to look a little bit more like that. And then the wavelength will be the same as this. So, yeah. Let me see what else. So the next thing we have is the Doppler effect. So this is basically, I'm not going to go into too much detail with this, but I'm going to just say we have a source here, and it's shooting out some sound waves, and then we have an observer here. And so basically, depending on where the velocity of this source is, if it's like there and the observer's there, basically these waves are going to sound faster or slower. And so basically, to determine whether we're adding or subtracting, we have to think about, are both of these going towards each other? So let's start with the observer. So if the observer is going towards this, right? This will make the waves seem faster, right? Because if the wave's general velocity is heading in this direction, right? And the observer is heading there, from the observer's perspective, the velocity of the waves that they're seeing is going to be v, I'll say v1, v2. The velocity that this person's observing is going to be v1 plus v2. So in this case, if the observer is moving forward, we're going to want to have a plus on the top. And if the observer is moving backwards, then we have a minus. So then for the source, we can think about it this way. The source is moving towards the observer, and of course, the frequency is the frequency of the observer. So the frequency the observer observes. So basically, if it's going this way, the frequency the observer observes is going to be greater, basically, because if we think about it again, even if this isn't moving, the velocity is going to be greater if this person is moving while also talking or emitting a sound, right? And because velocity is equal to wavelength and frequency, that means the frequency that this person has will also be greater. So that means we need to make this frequency value bigger. So on the bottom, we're actually going to subtract it. So you might be like, why are you subtracting it if it's increasing it? Shouldn't we add it? Well, if we added a positive value to the value on the bottom, this will make the bottom bigger, which will make this smaller. So we're trying to make this bigger, so we need to make this smaller. So that's why we're subtracting it. And then vice versa, if the velocity is, instead of being pointed in this direction, pointing in that direction, we're going to add it on. Then if they're both still, then there is no velocity to the observer or the source, and then it's just going to be the speed of sound. And go over that, the v of the wave for the Doppler effect, we're only going to be looking at sound, I believe. So the v of the wave, unless it tells you otherwise, is going to be 343 meters per second. This is at 20 degrees Celsius through air and at sea level. But that's a all right thing to assume if it's not provided on the test. You just remember that. So yeah, so v wave is the speed of sound, which is 343 meters per second. Okay. So now simple harmonic motion. So there are three parts of simple harmonic motion that he went over. It's periodic, so that means it's kind of it has periods, so it's like going back and forth. He said it's also like sinusoidal as a thing, so it could be modeled with like a sine or cosine. The displacement is proportional to the negative acceleration. So this basically means not equals. I'll just say proportional. So negative acceleration. So that's basically saying if we hypothetically have like a spring here getting pushed back and forth, the displacement it feels. Let's say this is the point of equilibrium. If this displacement is positive in this direction, the acceleration then, let's say displacement for a second is a vector. The x displacement vector is positive, assuming this is the positive side. And in that case, the acceleration is going to be wanting to push it back there. So, like the restoring force it's feeling is going to be wanting to push it back there. And so, also, just to touch on that, the restoring force is going to be just our force equation, which is negative kx, k being the spring constant, which has units of newtons per meter. Yes, yes, newtons per meter. And then x is going to have units of meters. So that's why it cancels out and makes forces. But x is going to be the displacement from equilibrium, basically, or the displacement from when it is measured. So like if there's already something on here, like say not a mass n, mass n, and then we're measuring the displacement after we add another mass, we're only going to be looking at the change from when we added the second mass if it's asking for that. So make sure you pay attention for that in questions. Don't let it trick you out. Regardless if it's an ideal spring, it shouldn't matter if there's already a billion pounds on it or if there's no pounds on it. It's still going to compress the same amount when you add a mass on it. And that's not how springs work in real life, unfortunately, at least most of the time. So yeah. And then we have a bunch of relationships here, which all relate to angular frequency, which we notice is the same as the angular velocity, and that's just because basically the frequency of the wave is or of not a wave but of harmonic motion is going to basically be the velocity kind of. That wasn't a great explanation, whatever. But I'll just go over some of the things he showed us. So it's equal to the square root of spring constant over mass, calculated using the cosine thing. I'm not going to show that here. I don't think we're going to be expected to know that. Hopefully not. It's also proportional to 2 pi over period. It's like a circle over time. And then 2 pi times the frequency. Kind of makes sense because it's angular frequency. It's also equal to theta over t. That was used in the cosine thing. And then also with a small angle approximation, I'm going to put a star next to this just to show that's not actually fully going to be that. Um, it's going to be square root of g over L. And then in terms of this was just used in one of those problems where it was asking for, it was like saying a spring being dropped here. What is its velocity after like or what's its maximum velocity or something? You can use this equation because basically the understanding that I have is that WR equals V. And if we think about it, if we're having some harmonic motion, even if it's not in a perfect circle, I'm drawing a circle just to make a point here. So you have a harmonic motion. The amplitude is actually going to be equal to the radius of the circle. So basically, we can say that relationship, and then we can also use the equation V equals square root k over m times a. which was necessary for one of the problems in the sheet. I think it was like problem 17 or something. I don't know. I already made a video on it if you want to see that. Yeah. In terms of simple harmonic motion, I think that is basically it for that. Um, other than like derivations and stuff, that's not. There's nothing really that crazy, I'd say, about that. Maybe also you'd want to know the equation a plus w squared x equals 0. But again, that was just how we related all these things together. But this is basically saying acceleration, basically the restoring force minus the mass, um, plus the angular frequency squared times the distance is equal to 0. That's the same thing as saying it's proportional to negative x, but then this is just our constant that we added in. Yeah, and let's see. Anything else for subharmonic motion? I'm probably missing stuff. Let me know if I am. But I'm gonna just be going over one second to last thing. I forgot to add a slide for this, but I'll just explain it also. Intensity. This was on a handout one day when he wasn't in class, but basically intensity is equal to power over area, or change in pressure squared over 2 times density times velocity of the wave. Of course, this is not really, I don't think we're really going to have to memorize this or use it, but just in case, I'll go over what this specifically means. So that change in pressure is basically I believe that's a max difference between like the maximum and minimum pressure. For instance, in like air, the density is going to be the density of the thing it's going through. So might be air, might not. Then velocity of the wave is just velocity of the wave. Power over area is a more general form of intensity. Um, I mean, I don't think we've ever used this, and I'm not sure if we ever will. But the important part is converting between intensity in watts per meter squared to decibels, because decibels is a logarithmic scale that we use to measure sound intensity. Um, you've probably heard it before. People are like, oh, that's 40 decibel sound, blah blah blah, whatever. So basically, to calculate this, you do log base 10 of the intensity that you're trying to convert over the IO, which is the lowest threshold. It's something like the lowest threshold for like intensity existing or something, but it's 10 to the negative 12 watts per meter squared. So you're going to plop that on the bottom. And then you're going to get a number of decibels. And the thing is, for sound, intensity is such a small number that decibels makes it easier to think of, because most of the time, all your answers are going to be like 10 to the negative 8, whatever watts per meter squared. Because if we think about it, like sound can't really exert that much work, I guess, on like a object that's like a meter squared, or like on a meter square stuff. I don't know, whatever. But it's basically not going to be that big of a number. So that's why I use decibels, since more like 40, 100, whatever. And so the last thing I'm going to go over is, check this out, linearization. Linearization. So basically, for this, he said it's probably going to be part of the test, I believe. So for this, basically, it's going to be like graphing. Yeesh. Graphing something versus something. Let's use an example here. How about frequency versus k, right? So frequency versus k. I'll just do a example sort of problem here. So if we're graphing frequency versus k, um and say we have like some data or something like that. Let me go back to that. Let's see. So root k over m equals 2 pi f. I should have that memorized. So root k over m equals 2 pi f. So if we're going to graph this hypothetically or experimentally, sorry, with k as the this thing and then f as this, I believe we're going to either get a parabola that's this way or a parabola that way. I forget which. But yeah, so basically we're going to get something that's not straight. And what we want is we want a straight line to make sense of our data. So how we're going to do it is we basically want to set it up in y equals mx plus b form. And in this case, I believe that most of the plus b's he's going to add are going to be so negligible or small that it doesn't really matter. As you can see, there isn't really any plus b sort of stuff going on over here. Experimentally, you might have a little bit of deviation. So there will be like a really, really small plus b. But for example, on my lab, my plus b was like 0.003 or something like that. So it's such a negligible amount that we don't have to worry about it, basically. I don't think he's gonna expect us to either. So basically, we have to set up our equation since in a form of y equals mx. So right now, what we see is we have our y here, and we have our x here. And this is giving us a parabolic thing. So instead, we want to graph it so that it'll be a straight line, like y equals mx, right? So if we look in this equation, our two variables, highlight in red, two variables, k, and we're comparing frequency. So if we look at these, there's a bunch of stuff around them. For each of these variables, I'm going to assign one. So this will be our x, and I already said this is our y, kind of how it was already graphed, right? And so basically, now what we're going to do is we're going to just solve for y to get it in this form. So solving for y, or k in this example, do it in blue, switch it up a little. Root k over m equals 2 pi f. So if we solve for k here using algebra, first thing we're going to do is square it. So then we have 4 pi squared f squared equals k over m. K over m. Oh wait, but we can just multiply by m, and then we get k equals 4 pi squared. I'm going to shove an m in there, f squared. So now you might be like, what? You just made a quadratic formula because it's f squared. But if we look at this, y equals mx, we can start lining up values. So we'll graph y as k in the y-axis. So we know we're going to have a graph with k versus something. So our slope is all of our constants, which is all this stuff, which is 4 pi squared m. So the slope should be whatever that comes out to be. Maybe it's like this. Maybe it's a negative thing if for some reason we have a negative mass. Not sure exactly how that would work out, but it's whatever. Then we're going to graph on the x-axis f squared. So now this will give us a straight line with the slope of 4 pi squared m. And say we want to find out the mass of our object for some reason, we could just plug it in and get out a mass. So yeah, that's basically it for this test. Let me know if I missed anything. I believe this is everything. I just looked through my notes. I was also absent a few days. I've been absent for like the past few days. So let me know if there was anything new we learned. But yeah, that's basically a general review of everything we've learned this unit, and good luck on the test, and see you tomorrow.